research by Dr. Matsumoto from Kyoto about numerical study of 3D Rayleigh-Taylor turbulence.
Thank you very much, and I'm very pleased to be here. Thank you for inviting me. Okay, so I will talk about the Rayleigh-Taylor turbulence. So I'm interested in disordered state in the central region of the Rayleigh-Taylor turbulence. The Rayleigh-Taylor turbulence. Okay. So by Rayleigh-Taylor turbulence, I mean the turbulence initiated by the Rayleigh-Taylor instability. Okay. So then I will measure these structure functions within this mixing zone. So this mixing zone, the size of the mixing zone evolves in time, it grows, and so these structure functions are time dependent, so that makes the problem interesting. So, and also there's a dimensional analysis result due to Sheltkov. So he argued these structure functions of the velocity and density scales like this way. So I would like to check whether this dimensional analysis is correct or not. Okay, so the starting point of this game is the so-called mixing zone length, and it is argued yesterday by Professor Young. So this length should grow as t squared. So that is first, as far as I've read somewhere, so it's first discovered by Fermi in 1950s. So here the important parameters appear. So this A is called Atwood number, and this numerical constant, which is non-dimensional, which is thought to be universal. So, so in this mixing zone, so the largest length scale grows like t squared. Then we can think there can be a possibility to use a similarity variable defined in this way. And also we are interested in the early stage of this mixing, so that we can expect the boundary effects are not important yet. Okay, so in my talk, I first check this law, because this is also the basis of the dimensional analysis due to Sheltkov. So then I move to calculate the structure functions of the velocity and density as long as this law holds. And in 2D, such comparison is already made by Celani, Mazzino, Vozera in 2006. And also there are many 3D Rayleigh-Taylor numerical simulations, for example, by Dr. Yang or Dr. Zhou. And there are many big players in this room. Okay, so the setting is the following. So this is the Navier-Stokes equation with a variable density. And I assume these diffusive constants and viscosity are the same for the two fluids. Then I scale the density in this way, so that this ρ1 and ρ2 value becomes -1 and 1. So here the Atwood number appears naturally. Okay, so now the non-dimensionalized equations looks like this. So we have here the buoyancy, or the effect of the gravitational force. And okay, so then I apply Buzynets approximation. So here the Buzynets approximation means I neglect this term. So this makes life very simple. Okay, so the equation I solve is this one. So the Buzynets approximated Navier-Stokes with incompressibility, and also the advection diffusion equation for the density. And the Atwood number I consider is 2. And I will remind you that the Buzynets approximation is valid for small Atwood number. And also the other important thing is I'm solving these equations under periodic boundary condition. Periodic boundary condition in all the directions. Some people may be a bit angry because this is density difference, plays the most important role. So this kind of periodic boundary condition can produce nonsense. But my excuse is that I'm only interested in the early stage of the mixing around this interface. So I stop the simulation at some early stage so that the boundary effect does not set in. Okay, so the initial condition is a step function plus some perturbation, as shown here. And the velocity is 0 everywhere. So the domain size, that will also matters. So I tried 2 different domain size with 2 different number of grids. So I used the 4th order Runge-Kutta method. Okay, so that's the snapshots. Okay, so I first check the mixing zone length law, whether or not it's really scales with t squared. So for that, I have to define the mixing zone length. So it's just empirical. I try not to be clever. Okay, so the mixing zone top is defined in this way. So the density varies just 1% of this density difference. Then I define that point as mixing zone top. The mixing zone bottom is defined also the same way. So if the density changes just 1% of this density difference, then I define that point as a bottom. So the mixing zone length is just the difference between the top and bottom. And then the simulation is stopped some early time. Okay, so this this red line shows the initial density profile. The density profile averaged over horizontal plane. So this blue one is just one snapshot, some instantaneous density profile. So I averaged this mixing zone length over different initial perturbations. So this is what I get. So it's a log-log plot. It's hard to see t-square law. Yeah, and so many people argue the reason why we don't see clear t-scaling law is just there's a subdominant correction, and this constant is quite small. And there are some people think that, so in order to see this t-square law, it's convenient to look at this object, which is also discussed in the Dr. Young's talk yesterday. So I plot this object as a function of time. So if this object becomes constant, then this implies this t-square law holds. So this object looks like this. So for some limited time, I think this t-square law holds in a rough sense. Okay, so this value around 0.04 is close to the different simulation by other groups. And also I tried different Atwood number. Atwood number appears here. So this object gives rather similar constant. So I'm sort of happy, and I enlarged the domain size. This red one is a small domain size. The blue one is the larger domain size. So the flat region seems to be extended a little bit. Okay, so so my conclusion is that this law holds roughly, and between for this Atwood number, so this t-square law holds, let's say from 20 to 40. Then during this time, I will measure the structure functions, and especially I'm interested in this temporal scaling. Okay, so I measure the velocity structure function and also the density structure functions, and the average, I will take the 2 averages. One average is a spatial average within the mixing zone within this region, and also I took the ensemble average over different initial perturbations. Okay, so this is these two are examples, and before showing my result, I'll just show you what the Sheltkov phenomenology goes. So the starting point of this t-square law, so the mixing zone grows like t squared. So based on this one, so we can define a large-scale velocity. It's just divided L, just divide L by t. So it's we can plug this one here, and then we have large-scale velocity grows like this. So then we can define the energy input at large scale. So this is defined with UL and L. UL is defined in here. And now we can define the, we can assume some kind of adiabaticity. That means the energy transfer rate at scale R, or energy dissipation rate at scale R, is the equal. And the important thing is the scale is different, but the value is same at the same instance. So that means the infinite speed of the cascade. Okay, then we can just dimensionally argue that the velocity difference scales like this way, and this epsilon r should be equal to epsilon L. So epsilon L is given here, so that we can have this kind of dimensional analysis. So the same thing can applied to be for the density difference. So we need the density dissipation rate. So density dissipation rate can be, okay, so let me start from here. So the density input rate at the scale L can be defined in this way. So the delta L is the density difference. And now we can argue this density difference can be dimensionally cooked up with this density dissipation rate and energy dissipation rate. Then we can get this kind of scaling. So it's a generalization of the Ovkov-Korsin scaling. So that's the result of the dimensional analysis. So I measure the pth order structure function and try to compare the measured structure, the exponents, and the prediction from the phenomenology. Okay, so this is the result for the longitudinal velocity differences. So of course the number of grids are not so many, so the scaling range is quite limited, so it's hard to see the scaling, but I can say at least for second order, the scaling, if it exists, so the scaling exponent is close to the dimensional analysis up to pico 4. So then I show two curves. The one, so the red here is a smaller domain, and green here is a larger domain. So for larger domain, it seems that the scaling range a little bit extended, but still the scaling exponent is somewhat close to the dimensional prediction. Okay, so now I'm going to the density structure functions. So here, for the second order structure function, the scaling exponent may be very close, but for pico 4 or pico 6, the scaling exponent can be quite different if you trust these figures. So again, I showed smaller domain and large domains at the same time. So it seems, yeah, there are some discrepancies for fourth order and sixth order. But if you trust the larger domain, there's a scaling here, then the exponent is quite different from the dimensional analysis. Okay, so so far I just showed for fixed time, and I'd like to look at the scaling in a spatial scale R. So for this spatial scaling, I can say for the velocity, this one, yeah, it's quite hard to say something because of the limited scaling range. But maybe I can say deviation from the phenomenology is quite small. But for the density, yeah, of course, the scaling range is quite limited, but still I can say deviation from the phenomenology is quite pronounced. Okay, now so far I looked at the density difference in an x direction, in the horizontal direction. So now I show you the density difference over vertical direction. So the vertical directions, the gravity is added. So if I subtract the mean temperature gradient, so that this temperature gradient can be defined in this way. So L is the mixing zone length, delta L is the density difference. So if I subtract this mean profile, then this fluctuation shows this kind of behavior. Okay, so then I like to see whether or not there's an isotropy. So I plot three different density structure functions. The increments, the direction of the increments are different. So the x direction, y direction, they are both horizontal plane. And also I plotted the zeta direction increments, but I subtracted the mean density profile. So this is the second order. There are three lines. They collapse each other. And for p equals 4, it's if you say, so this is the scaling range or inertial range, so they are quite close. And for p equals 6, the fluctuations are quite strong, so it's hard to say, but still, in a very crude sense, so their scaling may be quite close. Okay, so so my conclusion is that, okay, if you look at the scalar field, so the scalar is active now, but they are reasonably isotropic. Okay, now I'm going to temporal scaling. So I fixed the spatial scale r being 1 point something, so that is thought to be in the inertial range. So I fixed r and I plot these structure function as a function of time. So as you see, there's some kind of parallel behavior. If you believe this, for the second order, the slope is close to t to the power 1. So dimensional analysis is t to the 2/3. So it's quite different, even for low order structure functions. And again, I plotted smaller domain and larger domain at the same time. So the scalings are robust, and the difference from the dimensional analysis is quite large. And for the density, I did the same thing. I fixed the spatial scale r and plot the structure function as a function of time. So again, so this is a second order structure function. The measured scaling range, if you believe this, then the exponent is quite different from the dimensional analysis. And again, so this is smaller and larger domain structure functions shown in the same figure. So if you think the larger domain gives reasonable scaling here, yeah, it's quite wiggly, and it's hard to say qualitatively, but hard to say quantitatively, but they still, I think the temporal scaling deviates significantly from the dimensional analysis, even for the second order moments. Okay, so that's the summary of the temporal scaling. So the power law behavior is reasonably seen for some strange reason. For the velocity, it's quite good. For the density, it's a bit wiggly, but still we can say something. And the interesting thing is that even for the low order structure functions, disagreement is quite visible. So I'd like to discuss with you that is discrepancy is real or not. Okay, so I just add some final comments. So if I take the density structure function and compare the fourth order and sixth order moments, so the scaling in R and scaling in time, they are quite close. Well, I would say they are the same. So it's the exponent of R of exponent in time of the scalar seems to be as the order goes large, then the exponent seems to convert some constant. And in a statistically steady state turbulence, such saturation for the passive scalar problem is quite well known. So I think such saturation behavior is there in a time-dependent scalar turbulence. Okay, so this is my summary. And okay, so the small absolute number, I performed the numerical simulation of the Rayleigh-Taylor turbulence, and I checked this t-square law, and I calculated the velocity structure function and density structure function, and I measured the exponents, and the quality is not very good, but still I can argue there's some discrepancy from the phenomenology. So the outlook, is this anomalous scaling is real. So what is behind? So that's the question. And perhaps, so the assumption of adiabaticity is the first thing we can think of. And also, I think it may be some interesting that the Crichton model type analysis can be done with the time variable scalar gradient. Okay, so I'll stop here.
Thank you. We are even in advance from you, so there is time for questions.
Sitting next to Roberto, I'm of course triggered to ask a question about extended self-similarity.
Okay, so I didn't try
that
yet.
of course would be ideal to apply it here too, to extract
I
a
fully
better.
agree. Yes.
Did you try?
No, I didn't.
Other question? Oh, so
for the plot of alpha, seems like it's keep decreasing. Right? It's not saturated to a fixed point.
This one?
No, the plot earlier.
This one?
To get the alpha constant.
Oh yeah, okay, for the t-square law.
Right.
This one? Yeah.
Something like this. Yeah.
Yes.
It's not saturated. Right? It's not
Yeah, it's not.
Well,
It's not.
it's not going to a constant.
I think this can be caused by the finite size effect for the horizontal scale.
Okay. The box.
Yeah,
size
because
is that.
I enlarge the domain,
Okay.
then this decrease seems to stop. Yeah, for the larger domain, I don't have much ensemble, so the data is quite wiggly. But the trend says it's a finite size effect.
Seems like a transition from 0.04 to 0.02.
Around here?
Blue curve. Yeah.
Around this one?
Yeah, the blue curve. See, like you draw the 0.04, right? But to the end,
Okay.
it's more 0.02.
Okay. So you mean there's a flat region here and there?
Right.
Okay, so that's yeah, maybe. But I need more ensemble data.
no other question? Thank you.
In most of the flows this week, the dissipation of epsilon is presumably is only going very slowly. But here you've got epsilon, quarter to time. Plus does your scaling relate to the fact that epsilon is very rapidly increasing?
You mean the epsilon for the
The dissipation.
spatial averaged?
No, the dissipation rate, epsilon,
Yeah.
as you pointed out, is a quarter at a time, so it's rapidly increasing. Does the scaling or real over?
Dissipation rate.
Well,
Yeah.
yes.
Yeah, I don't think I plotted the dissipation rate as a function of time.
But you do quote the fact that it's quarter to time.
Yeah, it decays with some power in time.
Yeah.
Yeah. And that is close to the dimensional argument. Yeah.